Hello everyone, welcome to Pepcoding. So today in this video we are going to see that how to construct a binary tree from pre-order and post-order traversal. So here let's say this is a tree given to us. Let's write its pre-order and post-order. I'll just write its pre-order and post-order. I hope that there is no problem in writing of pre-order and post-order of these trees to you. Uh, just I'll just give a quick recap that how we used to write the pre-order. What we used to do, we used to draw these lines on the left side of every node, and then we used to start our Euler's path, and wherever this Euler's path was going to intersect with these lines, we used to write those values as it is. That is, we used to write those values in that order only. For here example, we used to write first the Euler's path is intersecting at A. We used to write A here, then B, then D, and so on. And for the post order, what we used to do, we used to draw lines at the left side of these nodes, right? And we used to do the same technique, that wherever this Euler path was going to intersect with these lines, these green lines, that is those are made on the left side. Wherever these lines are going to intersect these, this Euler path is going to intersect these green lines, we used to write in that order. For example, here D is going to come first and then F is going to come first. Why we used to do this? Because we know that this property is that for post order, first node is going to be visited, then left child, and then right child. And similarly for this, first left child, right child, and then node. So I'll just complete this pre-order and post-order array. Just give me 1 second. So here we have written the pre-order and post-order of this tree. Now what this question is asking us, that we will be provided with these two arrays and we have to create a tree something like this. And the one condition that is one constant is that this tree is going to be a full binary tree. As you can see that this tree is a full binary tree. So what is the definition of full binary tree? It is that every node is either going to have 0 children or 2 children, right? There is no child that is going to have 1 children. So let's start with the solution. What actually we are going to do? If I know that this first node is going to be the root node of from the tree, I'll just write it as it is, right? Now what we used to previously do, we used to previously find this A in the next given array, right? We used to find the IDX. We used to maintain an IDX, that is the count of the elements that was going to come in the left subtree and in the right subtree. But here if you see that this A is present at the last location, that is the last location of where? Last location of post order. So how to determine that which nodes are going to be in the left subtree and which nodes are going to be in the right subtree, right? There is no relation. But if you observe carefully, you can see that, or you know that the next element, that is in the pre-order, the next element that is going to come is going to be in the left part. As it is a full binary tree, it is going to be in the left subtree, and that is going to be the root node of that subtree, right? So here B is in the left subtree and B is the root node, or we can say that B is the parent node of this subtree, right? You can see this. So here, instead of finding A, what we are going to do, right now currently we are standing at A. Instead of finding A in the post order, we are going to find B. That is, we are going to find an element that is having one index more than it, right? Which means I'm going to find B. And here if I find B, somehow I found the total index of B. For here for this question, it is going to be at 4. Somehow I was able to find the index of B. Can I find the total number of elements that are going to be in the left subtree and that are going to be in the right subtree? Here we can see that these are the total number of elements that are going to be in the left subtree, right? I'll write it as left subtree. So to find that, can I write that if I have some pointers, let's say pointers are something like pre-orders starting index, pre-orders end index. Here post orders starting index and post orders end index. if I have these 4 pointers, right, what are these pointers? One is starting index of pre-order, second one is end index of the pre-order, then similarly post order starting index, post orders end index, and also we are going to maintain one IDX, that is index. This index is going to be of which index? This is going to be the index of the element, that is the next element of the root node, that is for this B, and that is that we are going to find in where? We are going to find in post order, that is the second given array, right? So here we are able to find B here, and index of B, this B was 4. So now is it possible for me to find out this total number of elements? These total number of elements are what? This left part is going to be my total number of elements that are going to lie in left part, right? That is going to be in my left subtree. So can I write here as it is going to start from where? It is going to start from post index, right? That is post orders starting index. So I'll just write it here as post instead of post order. Can I just say it is going to go from post order starting index to where? Here IDX was maintained, IDX, then to IDX till IDX, right? I can say this. So what is going to be the count? The count is going to be 0, sorry, 1 2 3 4 5. I have to include this B also. So here answer is coming 5. That is, I am trying to say is we are now going to calculate from post index, that is the element starting from the post index starting index, right? Sorry, post index, I am saying post, instead of post index I can say that post orders starting index to the IDX. So to get the formula, that is get the generalized formula, can I write here as IDX minus post orders starting index plus 1. Let's see if it is satisfying or not. For this condition, let's say IDX is 4. We'll just write it IDX as 4 minus. Currently my post order starting index is what? It is 0 and plus 1. Is it giving me the answer 5? And we have counted that from post index to IDX there are how many elements? There are 5 elements, and after using this formula we are getting the same answer. So we can say that this is the formula to get the total number of indexes or total number of elements, right? So what we are going to do now further, if I set my A as a root node, I am going to pick these elements, that is 5 elements, total number of elements, from this also, from this pre-orders array, that is 1 2 3 4 and 5, that is till G, and I am going to send them in where? I am going to send them in the left side of the A, that is in the left subtree. So it is going to be B, D, E, F and G. Similarly, I am going to pick these 5 elements including B in the post order. I am going to send here. So these are going to be D, F, G, E, B. Now similarly, the remaining elements, that is from C to M are going to lie in where? Are going to lie in the right subtree of this A, right? So we are going to send them as it is C, H, I, J, K, L, M, and similarly we are going to send these elements. Now this is a important point to notice, that we are not going to send the rest of the elements. We are not going to send all the elements of the post order in the right subtree, but we are going to send elements that are starting from this point, that is IDX plus 1, that are starting from the next point of the IDX till the last elements, till 1 less than last element, that is till this point, till C. Why? Because A is already included at the beginning, at the main root node, right? So we know that in the post order there are as we have discussed, this is the main property. What was this property? First we are going to visit node, then left, then right. Here where we are going to visit first left, then right, and then node. So here node is always going to come in the last position, right? Therefore we are not going to include this in our right subtree, that is we are not going to include A in our right subtree. So we are going to send till where? From H to C. So H H, J, L, M, K, I, and C. Nice. From here, now we are going to do the same things again. We know that this B is going to be set as the root node in the left subtree, and for this part, C is going to be set as the root node, because this is our pre-order, this is our post order. Pre, post. Now our starting index, pre-order starting index is going to be this pre-order starting index, end index is going to be this post orders, so pre-orders end index. Now what is this pre-orders end index actually? It is nothing but nothing but total number of elements plus this previous pre-order starting index, right? We will talk about this later. For now, just remember that this is going to be our, let's erase this. For now, just remember that this is now going to be our new pre-orders end index, and similarly here this is going to be start index, this is going to be end index, and similarly for these two also, post orders start index, post orders end index, post orders start index, post orders end index, right? Now what we are going to do, we are going to set this B as the root node, C as the root node, right? Now we are going to find where this B is going to lie in the post order, and we are going to maintain a count. But again, as we have did in the previous for A, we are not going to search for this B, we are going to search for the next element of the B, that is going to be this D. So we are going to search D in the post order, we are getting D here, therefore we are going to send this, D and its count in the left part. So what are the values before D in the post order? There are no values, so D is going to go as it is, and similarly here D is going to go as it is from pre-order and post order. Now remaining rest values are going to go in where? Are going to go in the right subtree. So it is going to be E, F, G, and it is going to be F, G, E. Why not B? Because this is the root node that we have already included, right? This is our root node we have already included. And for C, what we are going to do, we are going to search for the next element of the C, that is H in the post order, and we are going to send its value before H, including H, in the left subtree, and after remaining values, that is values after H till one less from the last in the right subtree. So here values before H are nothing, so we are going to send H as it is, that is H and H, and before these values, those are going to be here till here to till here. So these are going to be what? J, sorry, not J, H, I, J, K, L, M. Similarly, here we are going to send what? We are going to send J, L, M, K, I, right? So let's say 1, 2, 3, 4, 5, and 6 values, right? Now again we are going to follow the same steps. For here, D is going to be set as the root node. Here A is going to be set as the root node or the main node for this family. For the below family, H is going to be set as the main family node, head node, and this is going here instead of this H. Oh, this H is not going to come. Sorry, this I is going to be set as the root node. Let's say 1, 2, 3, 4, 5. Right now this is right. Previously we counted incorrectly. Now I is going to be set as the root node. So here D is set as the root node, E is set as the root node, H is set as the root node, and I is set as the root node. We can also call this as the head node for this current family. So here in D's family there is no values present in the array. Therefore D is going to be the end node of this family, right? Here for E, F and G are remaining, and here also if I say F and G are remaining, right? So here we'll be finding value value 1 next, that is we are going to find for f in the post order. So here we are going to send f, that is f, and before it's, and here we are going to send g. As you can see that these two are going to lie on left and right side, right? So here f is going to go and g is going to go. Why f is going to be alone? Because previous values of f are nothing, so f is going to be included singly, and here therefore this f is also going to be included singly because total number of elements is going to be 1 only, and so on. G is going to get here, right? Now h is also the final node of this family. Now for this particular tree, this particular subfamily, subtree, what is going to be? We are going to find j in this post orders array. So here we are finding j here. So j is going to be here. The count of total number of elements is going to be 1 only. So j is going to be here. Now similarly, here what are the remaining values are going to be included here? Those are what? Those are KLMN, KLM, and here it is going to be LM, K, right? Why not I? Because I is already been included. Now we are going to do what? Same thing. F is being set. F has been declared as the head node. G has been declared as the root node, right? F, G. Here J is declared as the root node. Here which node will be declared as the root node? K will be declared as the root node. We are going to find an element for L in the subtree, that is going to be here LL, and here it is going to be what? It is going to be remaining of, that is M. So here we can say that L and M are going to be set as the root node. If we circle this for our better understanding, you can see that our array has been totally used. Therefore this means that our tree is fully made. Now let's try to compare these values with our previous tree, right? I'll just try to fit this in. Okay, if you bring this array here, bring this tree here, and we try start comparing the values, we can see that A as the root node, then B was the second root node or second main node of the left subtree. So that is here, right? C is going to be here, C is going to be here, D is going to be alone, D is going to be alone. E is going to have two children, F and G. E is going to have two children, F and G, right? Now C is going to have one children, H, that is going to be alone, and second child as I, that is going to have some children. The first child is going to be J, and second child is K, Now K is having L and M. So with this we can see that our tree has been constructed fully. Now what was the logic behind this construction? I'll discuss it once again because I think this is necessary. What we are going to do, actually we are going to set the first node in the pre-orders array as the root node. Okay, so this node is going to be set as the A is going to be set as the first node, and now we are going to search for the next node, this or next value of pre-order in the post order, that is we are going to search for B, and somehow we are able to find the count, that is somehow we are able to get the index of the B in the post order. We'll be able to find the count, that is total number of elements that are going to lie in the left subtree, because we have to find the total number of elements with respect to, or total number of elements before B in post order, right? Before B in post order, that is these values. And if we get those values, we know that these values, that is these values, are going to be in the left subtree, and remaining values one less than the last value, that is one less than last value, because A is already considered here. So these values are going to lie in a right subtree. So what is actually going to be, if I try to simplify this and I say that if this is my root node, if this is my root, at any point, if this is my root, then if I have some pointers like pre-order starting index, pre-order end index, and post-order starting index, sorry, post-order starting index, post-order end index, and then two more pointers, that is IDX, and one value that is going to be total number of elements. So using these values, can I say that first for in the left side, what is going to go? It is going to be that from this value, from P, that is one value extra than my starting index. Initially my starting pre-order starting index is going to be 0. This is going to be n-1, that is the size -1, right? This is also going to be 0, and this is also going to be n-1, right? Index is starting initially it is going to be 0 only, and total number of elements we are going to find out. So initially, can I say that instead of sending 0 here, what I am going to send? I am going to send the next element of the pre-order starting index. So I am going to send next element of the pre-order starting index, right? And the end point, that is the end index for this subtree, is going to be what? This subtree is going to be total number of, if I say total number of elements, that is this point, that is just these values, total number of elements. So can I say that total number of elements, but before that I have to add this in my starting index, total number of elements. So let's see if it is giving me the right answer or not. Initially my starting index was 0, and what I sent as a starting index for the left subtree, that is for this, it is going to be 1, right? This is my starting index, this is my end index. So my end index is going to be sent as what? My end index is going to be sent as total number of elements. What was my total number of elements? That was 5, plus this 0, that is going to be what? That is going to be 5. Let's check. Is the index 5 is the index 5 going to be included? Yes, this you can see that this is going to be included. So till this point, till this 5, it is going to be included in this left subtree for this question. So therefore we can say that this formula, or this expression, is going to work. Now similarly, for my post order, what is going to be sent as in my post order? My starting index is going to be as it is. So can I write here as my starting index of post order as it is? Till when I have to till what point I have to include my values? If you remember, we have to include this values till this IDX, right? Till this IDX. So can I say that my end index is going to be what? My end index is going to be IDX, right? Now if I know the starting index and end index of the left subtree, can I find out my starting index and end index of my right subtree? Yes, we can easily find out. What is it is going to be? Obviously the starting index for my left subtree is going to be one more than the end index of the my right subtree. So I'll rephrase. Previously I said wrong. I'll rephrase it. What I am saying is, my starting index for this right subtree is going to be one more than the end index of my left subtree, right? Let's write this. My starting index is going to be one more than the end index of my left subtree. What was my end index of my left subtree? It was PSI, that is starting index plus total number of elements, plus 1. This is going to be what? This is going to be my starting index. And what is going to be my end index for pre-order? It is going to be nothing but n-1. And what was this n-1? This was my end index of pre-order, right? Now similarly, for this post order, that is also going to be same. That is also going to be the same value, that is IDX plus 1. It is going to start from IDX plus 1 until when? Till which point? Here you can see that IDX was still here. We have to start from here, but we have to end here. That is one less than from the last value. Therefore we are going to write here what? We can write it as n minus 1, or we can write as till post orders end index -1. So with this, with these values or with these pointers, I can construct my whole binary tree using these values and these pointers. Right, now let's try to code this. I hope the explanation part was clear to you all. How actually we did, we just instead of looking here and there, or I'll say that instead of looking directly for the root value in the post order, we searched for the next value in the post order. That is, we directly searched for which value? We directly searched for B. Instead of searching for A, we directly search for B in this whole array, and using that IDX point, that is using the position of this B in the post order, we were able to find the total number of elements that we can send in the left subtree, and that after those we can send in the right subtree. Right, so let's try to code this thing, and after that you'll be able to understand more clearly. And after that we are going to discuss one more thing, that is going to be why it is compulsory to have a full binary tree for this question, like how these properties are actually useful to us and how these properties are going to help us in the future questions. So let's code this. Let's code this question. Okay, so here, as we see, what we are receiving a array of pre-order and post-order. Okay, now what we are going to do, first let's take the size, and the size is going to be same for both the arrays. So we'll be just using pre dot length. Okay, now we are going to return something that is going to be received from a function. Let's call it as buil tree builder or build tree, build tree. Right, and in this function what we are going to pass, we are going to pass our pre-order, that is array from pre-order, our starting index, that is going to be 0, our end index, that is going to be n-1, and second thing we are going to pass as post order, that is our post order array with index 0 starting index and end index as what, n-1 again. Right, we are going to receive something from this function, and we are going to return this to our main function. Now let's write this function. What this function is going to be: public static tree node build tree. And what this function is going to receive, it is going to receive an array of pre-order, name it as pre-order, an integer value that is going to be starting index of this pre-order, and again another integer that is going to be a end index of this pre-order. So end index of this pre-order, then again it is going to receive an array of post-order, then it is going to receive an integer that is going to be post-order end index, so starting index, and another integer that is going to be post orders end index. Right, now what we have to do, as we first come in this this function, what are we going to do? First we are going to create a node with value what, with value a. That value is lying where, in the pre-order. So with the first value of pre-order, that is with the value of starting index of post or pre-order, we are going to create a new node. So let's name it as pre-node is equals to node is equals to new node with values what, with values pre-order starting index. So pre-order starting index, so it is going to be psi. Now what we are going to do, second thing we are going to do is we are going to search for the next value. As we have discussed previously, we are going to search for this b where, in this post orders array. So we are going to search, first we are going to write create an index that is going to be 0 initially, or let's say instead of 0, let's say it is lying at this position, that is post order starting index, right? Now we will be using a while loop. Sorry, while loop. In this while loop, till when we are going, till what point we are going to travel, till our IDX in the post order is not equal to the value of IDX in the post order is not equal to the pre-order, the orders starting index plus 1. Why plus 1? Because we want to check for this next element, that is this B element. So till this element, till we don't reach to this element, we are going to travel, right? So here we are going to increase our IDX, right? Now what is our next step going to be? As we have found the IDX, we are going to count our total number of elements. That is, we are going to count, if I am able to find my IDX, that is, if I am able to find my this IDX, I am going to find this total number of remaining elements. And what was the formula we were using? We were using that IDX minus the starting index of the post order plus 1. So we are going to just do that, IDX minus post order starting index plus 1, right? Now we got the total number of elements. Now what we have to do? We have to just make calls. So node.left is equals to build tree. What will be calls? What will be passing in this calls? We are going to pass our first preorder. Sorry, preorder. Then the starting index. What is now starting index going to be? As you can observe that we have used this A. Now my starting index is going to be what? Here we have written. Second, I'll show you. Here we have written what? Here we have written starting index as starting index. But as you can observe that this A is already been used. So am I going to pass the starting index as it is? That is, it is going to be passed as 0. No, it is not going to be passed as 0, because I will be passing it as 1, starting index plus 1, because now we are starting our next, or we are starting to build our tree, that is left subtree, with the next index, the value at the next index. Therefore we are going to pass starting index plus 1. So let's just pass this thing. So instead of passing just PSI, we are going to pass PSI plus 1, that is starting index of post order plus 1. Next thing, what we are going to pass? Next, what is going to be our end index? We have to travel till what? Our end index is going to be PSI plus TNEL, that is total number of elements. Let's see if it is true or not. If I say that starting index is nothing but 0 here, plus total number of elements is what? Total number of elements is 5 here, right? As we have discussed for this question, if I do this, I am getting total number of elements as 5. So if I pass my next element or next index as 5, am I going to get the correct value? Let's see, 1 2 3 4 5, and obviously the next elements has to be this part, that is from B to G, right? That is going to be in our left subtree, right? So we are going to pass this as it is, as we have wrote. So it is going to be PSI plus total number of elements, right? Now what we are going to pass? We are going to pass post order, that is array of post order. Then the starting index of post order is going to be what? It is not going to be plus 1, because it is going to be as it is. So we are going to pass it as it is. So post order starting index, yes, post order starting index. And now what is going to be the end index, or we can say that till what point we are going to send it. So we can say that till this point we are going to send it, that is till IDX, right? IDX is being maintained on that point. So we are going to send till IDX, right? Now this is for left call. Let's first return node from here. Now for the right call, that is for the right subtree, we are going to pass what? For right subtree, total number of, sorry, the starting index is going to be what? The starting index is going to be one more than the previous end index, as we have wrote here. That is, next are for this right subtree, that is going to be starting index plus TNEL plus 1, that is one more than this end index, right? So we are going to pass it as it is. Sorry, yes, end index is going to be nothing but our, where is our starting index? It is going to be plus TNEL plus 1, right? These are going to be starting index. Now what is going to be our end index? Here, as you have seen, instead of this return thing, I'll just show you our end index, as we have wrote here end index. But why we are sending end index? Because now you can see that from this point, as we have wrote that, as we have wrote what? We have wrote that TNEL plus the previous end index, that is plus PSI, plus now what we are till what point we are going to send? Plus 1, that is from this point, and we are jumping to this point. From this point we have to send till this point, that is going to be what? That is going to be same as the end index for pre-order. It is easy. So our end index is going to be what? Here it is going to be PSI, starting index plus 1, and our end index is going to be, I'll just erase this thing. Our end index is going to be what? PSI, pre-orders end index, so PEI, right? Now we are going to pass our post order, and starting index for this post order, that is for the right subtree, is going to be what? Or right subtree is going to be from IDX, that is IDX plus 1, right? First we will write this IDX plus 1. Now, and similar to this, is my end index going to be this? So can I say that my end index is going to be something like this? Post orders end index. But is it going to return me the correct value? I say no. Why no? Because if I pass the end index as it is, that is the post orders end index, it is going to include what? It is going to include this A, and we don't want to include this A, because A is already been consumed here, right, as the root node. So instead of this end index, we are going to just return, or we are going to just pass a one value less than that end index, that is going to be C. So here we are passing C. Now with this, our function is completed. Now our base case, what is our base case going to be? Our base case is going to be if my starting index of pre-order is greater than my end index of my pre-order, that is end index, return null, right? Similarly, if my what, if there is only one node, that is if PSI is equal to, that is starting index of pre-order is equal to end index of pre-order, that is PEI, then do what? Then just return, or instead of writing here, I'll just write this base case here. Instead of passing here, I'll just write here node. Now what this thing is doing, this line is doing nothing but if it is saying that if there is only one node, that is PSI starting index is equal to end index, this means that there is only one node. Let's say it is only one, and pre-order of this is going to be 1, post order is also going to be 1. Therefore I'll just create a new node and I'll just return that. So it is just doing that. We have already created a node and we are just returning this node. So with this, our code is complete. Let's try to run this and see if there are any syntactical errors or not. So yes, there is an error, not a statement. Okay, we have to pass a return here. Return node. Let's now try to run this code, and output comes here. it is not actually printing anything. Let's see why. Node dot right, preorder. Okay, till n is not equal to node dot left. Yeah, okay, the calls are correct. Let's check from the starting. There is a silly mistake. What is that silly mistake? It is not actually printing any answer, which means that it is not able to find the index. That is, yes, here instead of this we are going to write post order, because we have to search in the post order, right? I hope the error was clear to you all. Now let's try to run this code. It is giving us the successful command. Let's try to run this code and see if all the test cases, yes, all the test cases are passing. So with this, I hope the code is also clear to you. Now I want to discuss one thing with you, that this is going to be a very important thing for future questions also, that why this property is important, why this property of for pre-order and for in order and for post order, why this property is important of first we visit what. In this we are going to visit first node, then left, then right. Here we used to visit first left, then node, then right. Here we used to visit what, first left, right, and node, right? So why this property is actually important to us, and why this constant was given, why this constant was given in this question, that if you want to create a binary tree using pre-order and post-order, then the binary tree, that is these two arrays given, should be a complete binary tree, should form a complete binary tree. Why this thing was given, I'll give you an example, and by that example you will be able to understand. Let's say, what will be the pre-order and post-order of these trees? 1, 2, 3, 4. If you observe these two trees carefully and try to write their pre-order and post-order, these trees are not a complete binary tree. Why not a complete binary tree? But because, as by the definition of the complete binary tree, the binary tree or the node should have at least, the node should have either 0 childs or 2 childs, right? So here you can see that this current node, this one node is not having any child, any second child. Okay, it is only having one child, right, in both the trees. As we can visualize that these both trees are different. But if we try to find out pre-order for these both trees and post-order for these both trees, we will be able to understand that why actually a complete binary tree should be necessary to construct a binary tree using pre-order and post-order. What is going to be pre-order for this binary tree? This is going to be what, 1, 2, 3, 4. Same here, it is going to be 1, 2, 3, 4, right? 1, 2, 3, and 4. Now what is going to be post-order here? The post-order is going to be 3, 4, 2, 1, 3, 4, 2, 1. Now what is going to be the post-order for this node, this tree? It is going to be 3, 4, 2, 1. Now if you observe carefully, these two values are coming as it is, like these two values are matching each other, right? So if the examiner doesn't give me, or if anyone doesn't give me the constraint that the binary tree should be a full binary tree, then there can be two possible solutions for these kind of trees. Like there are n number of possibilities, or we can say that there are n number of examples just like this, where we'll be finding same solution for two different trees. Therefore with this we can say that a binary tree or a complete binary tree has a unique solution. This statement is being proven by this thing, that is, if a tree is not a complete binary tree, then that might give a same answer as some other tree, and if it is a complete binary tree, it is going to give us a unique solution. Let's try to see this, if it is giving us a unique solution or not. Let's add some node, let's say 5 here, and here also let's add 5 here. Okay, now if we again calculate the pre-order and post-order for these trees, we can see that for this tree the pre-order is going to be what, 1, 2, 3, 4, and 5, and post-order is going to be what, 3, 4, 2 5 1. Pre-order is going to be what? 1 5 2 3 4. Post order is going to be what? Post order is going to be 5 and then 3 4 2 1. Now you can observe that these two values are different. So if I give you these two values, then you will be able to construct a binary tree that will be having a unique solution, because these two are obviously different. Therefore these properties are really important for us. These properties actually give us the abstraction that how using these properties we can create a binary tree, or how using these properties we can perform operations on a binary tree. And that also, it also tells us that a binary tree, a binary tree that is a complete binary tree, will have only one unique solutions for pre-order, post-order, and in order, right? And if it is not a complete binary tree, it might have same answers to some other incomplete binary tree, right? So with this, I hope the video was clear to you all, and also the question was clear to you all. So thank you for this video. Let's meet in the next video.